One of the most successful things about physics, even in this class, in particular mechanics, is the ability to predict motion or predicting motion. Now you got to be a little bit careful with the word predicting, because that implies you're looking into the future and trying to say what's going to happen, which we know is impossible because no one can know what's in the future, but it turns out that theories of physics that we have been very successful at doing this. For instance, we can send space probes to the moon by predicting where the planets are going to be and where the space probe is going to be. We can send the space probe to Mars. We can understand how airplanes fly enough to build them and operate them safely. We can predict the positions of our cars and so on and so forth. So the idea of predicting motion of everyday objects is pretty successful, and that's one of the core themes of this class, is so you can learn a little bit about motion enough to predict, say, where something's going to be. As an example of this, we'll just choose a very extremely simple object, a ball. And let's say that the ball's position is given by where that dot is right there, and I've drawn a little structure around it like that. And it turns out that probably the most basic thing we can label the ball with in its motion is that it has some position along the horizontal, which we'll call x, and it has some speed at which it's moving v, and it has some acceleration a. Now, any of these three things, or even all of them, can be zero, but you don't discount zero as being sort of a non-player in the game. It just means that it happens to be zero. So you could say something has no velocity, but that v would just be equal to zero, and it's still a number that can be dealt with, or something can have no acceleration, which means a is zero, but nonetheless, you still can say it has all three of these things, a position, a speed, and an acceleration. Furthermore, when we're looking at an object and we're about to predict where it's going to be, we sort of call this situation right here, you can call this the current position of the object, or sometimes it's called the initial position of the object. Initial position. Now, initial can be a little bit misleading because a prediction doesn't always have to start at the very beginning of the problem. You might have a problem or a motion that's about halfway through and you still want to continue to predict where the object's going to be. So I prefer to refer to as the current position of the object. Now, we have some special notation for x, v, and a when we're talking about the current position. In particular, instead of x, we'll write a little zero right here and pronounce it x naught or x zero. And for v, we'll pronounce that v0 or v naught. And yes, I am saying naught here. I think you can sort of think of it as N-O-T, so V naught. That's what I'm saying here. Now, it turns out maybe we should put an A naught on there, but that's sort of a restriction of the class. We don't really have accelerations that are going to change during a prediction cycle. So A will be A throughout the prediction, so we'll just leave it as A. We won't refer to it as A naught. Now, in the idea of doing this prediction then, what happens next is a little bit of time can go by. Now, this is not the right sort of format to try to draw time on, because this is all a spatial thing. This arrow that I've drawn is 3 inches over this way. It doesn't represent time. There's no way of representing time unless I took this board and say threw it off and got another board and said these two boards existed 1 second apart. Nevertheless, try to imagine that we let a little bit of delta t, a little bit of time go by, like a second or a half a second or even a minute or an hour or something, and we'd like to predict where this object is after that delta t has elapsed. So we'll draw another object here. It's the same thing, the same sphere. There's the position of the sphere. But what has happened now is the sphere has obviously moved. Some time has gone by. It's moved. And I'd like to know where it is now. That's the business of predicting motion here. We give it a new set of variables. Instead of x naught, v naught, and a, we'll just call this new position x. We'll call this new speed v. And we'll call the acceleration a. And as I'm saying, there's sort of a constraint of physics at this level that this A will always be the same as this A insofar as these problems go. Now, A may abruptly change later, but at least over our prediction cycle, A will be the same. But note that x is no longer equal to x naught. That's why we need the different notation. And v is no longer the same as v naught. That's why we need a different notation on that. Now, I say they're not the same. They could very well be the same if something didn't change. But in general, predicting, we'd expect a new position, maybe new velocity, depending on what the situation is. So we'll just leave it at that. This is one of the real powers of physics then, is to be able to say, okay, look, if an object is sitting here at some initial position with some initial speed and some acceleration, and then we let a little bit of time go by, what will its new position, new speed, and acceleration be? The way those things are connected then are via the three equations that we discussed in another video or at some other point in class. In particular, x, the new position over here, is equal to x naught, the old position, plus v0 delta t plus 1/2 a times delta t squared. There's one of your prediction equations you can use. This equation, in fact, tells you where the object is going to be in the future. Now, as a condition of telling you where the object is going to be in the future, you have to know where it is right now. That's x naught, its current position. You have to know its current speed. You have to know its acceleration. And you also have to know how long of a time interval you want to elapse for that prediction to occur. But if you know all those things, this equation very happily gives you x, the new position at some future point in time. That just tells you where the new position will be. You might also be curious about what the new speed will be. Well, that will be given by v naught plus a times delta t. So in other words, physics can also tell you how fast the object will predict that new speed the object will have at some time in the future, but all you have to know is v naught, its current velocity. And again, you have to know what the acceleration is on it right there, and you have to know how much time you want in the future you'd like to make this prediction. That's always what the delta t is going to be. So, with those two equations, you can predict if an object is here with x naught, v naught, and a, what it's going to have a delta t in the future. And that's what I mean by physics has been very powerful in predicting motion. Even at this level, you can predict where an object's going to be. Notice the equations are kind of particular, and that the very, very left sides of them here sort of has the future variables, the x and the v. Now these are the variables that are over here at the new position, not the old one. Those are the x and the v. What are they functions of? Well, over here on the right-hand side, you have the x naught and the v naught, and there's a v naught right there. And you have the a and the a. All of these other variables over here are sort of what exist at the current position of the ball or the object. So that's the way the prediction works. If you know where it is right now, and you know the parameters of it, and you want to know where it is in the future, you can take all that right now stuff and put it on the right-hand side of the equation, do some computation, and the equation will spit out where the object is some dt in the future. So that's what we mean then by physics being able to predict motion. We can tell where an object is going to be some delta t in the future using these two equations and information about where it is at this particular instant.